Hello, and welcome to another video in this series as together we learn Lean in order to write simple mathematical proofs. So over the last few videos we've done some simple things with Lean. We got used to the idea of writing proofs in code in Lean, and we saw simple mathematical challenges, and we saw how they translated into a proof. And we did things like, sort of inequalities and substitution. And in the last video, we actually stepped up a little bit and did a little bit of algebra. Today, we're going to be looking at inequalities, but different to what we've seen before, because it can present an interesting challenge for both us and a theorem proof assistant. So let's kind of talk a little bit about why that might be. So in the very first video, we had a very simple task. I think it was something like a equals 4, prove that a is more than 1. So essentially proving that 4 is more than 1. So the final line in the proof was to show that 4 is more than 1. And we talked a little bit about why that is the case. 4 is more than 1. Sounds obvious, doesn't it? But we also talked about, we could go all the way back to the axioms, but we then, in everyday proofs, we don't need to do that. But it was a simple numerical comparison. So that proof, that inequality was right at the end. What we're going to look at today is where the inequalities in the middle or at the start of a kind of a proof. Let me draw a picture to kind of explain what that means. So previously we had something like, a equals 4, prove that a is more than 1, which turned into 4 is more than 1, and that was the final line of the proof, and that was done by the properties of natural numbers. These are all natural numbers. What we want to do today, and these are the hypotheses, these are the kind of given facts. Today what we're going to do is have inequalities in the given facts, in the hypotheses. So we may have something like, I don't know, a is more than 5, and maybe something else, and then we have to prove maybe a result that says b is more than 10, perhaps. But the interesting thing here is that this time the inequality is right up front at the beginning of the proof, and it has to work its way through to the conclusion. So that's what's different. So here we just had something, I don't know, equals maybe 5, and then we have to just prove that's more than 1. That's the last line of the proof. So there's no inequalities for the rest of the proof. It's just at the end. So that's an easier scenario, whereas this is a little bit more challenging. And what's interesting here is that if we have a theorem that has some kind of assumptions, the kind of given facts or the hypotheses, and a conclusion, and let's say it says whenever a is more than 2, I don't know, z is more than 100. This is more general than saying a is 4 and 4 is more than 1, or even a is 4 implies z equals 6, something like that, because the hypothesis here, a can be anything as long as it's more than 2. It could be 3, 4, 5, 10, 12, 200. So the kind of the input is pretty broad, and so is the output. So it's kind of a more, inequalities allow us to have more general theorems. So that's what we've said here. If you want to, you can always download these slides and kind of read them in your own time, or look at the blog, which is written a little bit more carefully. At the moment I'm just talking to you off the top of my head, but the blog will be written in words that are more carefully thought out. So let's look at a really simple task. We always try to keep things simple because our focus is on learning Lean, not to get bogged down with mathematical kind of puzzles and challenges and tricks. So given b is a squared, and also that a is more than or equal to 2, so a could be 2, 3, 4, 5, 10, 100, anything as long as it's equal to or above 2. Our task is to show that b is at least 4, b is more than or equal to 4. Now, in our heads we can do this. This is really easy. The thinking could be something like, the smallest value that a could be is 2. So b is a squared, b is 4. So the smallest value that b could be is 4, which kind of translates into that conclusion. But as we've said before, the purpose of doing these simple tasks is to try and train ourselves to write structured proofs that are easily translatable into lean proofs. So we have to kind of get through that kind of challenge where something is so easy we almost zoom through or skip over the details because the answer is so obvious. So that'll always be the challenge for us. So again, just thinking about what we've said earlier about theorems that involve inequalities, that conclusion holds. This conclusion, if it's true, holds for any a as long as it's more than or equal to 2. So it's quite broad. So there's something different then about this task compared to the very first chapter. There's something very different, and that will translate into something different about the proof as well. So here's an attempt at writing a structured proof. Notice a good habit of writing the hypotheses right up front, the given facts. So b equals a squared is given, a is more than or equal to 2 is given, and then we're into the meat of the argument. So we say we want to prove something about b, so it's kind of a good strategy to write down b. It isn't always the best strategy, but for many simple proofs it is. So b equals, well, what does it equal? Well, we know that it's a squared. We make it explicit to say it's using fact 1. That's a good habit to get into. I know it sounds obvious, but this is how we'll translate it into lean code. And then we say, well, we want to prove eventually that b is more than or equal to 4, but all we've got here is a squared, and a itself doesn't help us. We want to kind of get rid of it or resolve it in some way. Is there another fact that can help us? Well, there is. This one, a is more than or equal to 2. So if a is more than or equal to 2, we can almost do a kind of a substitution. More than or equal 2 squared. We do have to be a bit careful there, so we'll talk about that in a minute. But this is one of the things where it's kind of obvious, so we sometimes skip over the detail. But we'll come back to this. We won't gloss over it too much. And then we say this quantity 2 squared is 4, and that completes the proof. But there's a couple of interesting things worth pointing out. That first thing was that jump from a is more than 2. Let's go back to it. A is more than 2. We use that to say a squared is more than or equal to 2 squared. So a is more than 2. A is more than or equal to 2. We went from there to a squared is more than 2 squared. Now, that, yes, again, that's really obvious. But let's think about why that's valid. Why is that true? Because inequalities can sometimes trip us up sometimes, particularly if there are things like negative multiplication in there. You can swap the order, you can flip the direction of the inequality, for example. So on this one, yeah, you probably didn't think about it. Now, I admit I didn't think about it a lot on the first go, but when rereading it I thought, hang on, there's something else going on here. Why are we so comfortable in saying that's true? So we could, again, go all the way back to the axioms and kind of rebuild our justification from the very basic bricks, as it were. But actually, in everyday proofs, we're happy to say that actually it's a well-known, commonly accepted fundamental result that if m is less than n, these are natural numbers, then m to the I is less than or equal to n to the I, as long as I is a natural number. Now, natural numbers also means that they're not negative, so that helps us keep things simple a lot here. If these were integers, then things could get a little bit more interesting. So these are natural numbers, so everything's going to be positive. So that's almost an identity that we can point to and say that's always true. Now, somebody will have done the work to prove that's true. But this kind of mini theorem, this lemma, is it's okay for us to kind of refer to. The crucial thing here is that this is natural numbers. As I said, if it was integers, which could be negative numbers, then things can get a little bit more interesting. Cool. So it is worth thinking a little bit about, how we did that, and it'll help us when we write Lean code, because we'll have to think about how would Lean do it. Lean at some point has to justify this step as well. Let me just draw a picture of that, just because I think there's a lot of writing on the screen and it isn't always clear. So we were given a is more than or equal to 2, and we want to say a squared is more than or equal to 2 squared. And yes, it's obvious, but in terms of some kind of justification, we're referring to a commonly agreed, identity, a theorem, a lemma, that says if I've got two numbers, natural numbers, m, and if m is less than or equal to n, then m, let's call it p for power, is less than or equal to n power, as long as they are all m, n, p natural numbers. So this thing is true, and we could go and prove that, but we're fine for now. So this is something that we can reuse, and that's the reason we can justify that step. The other interesting thing about this proof is that it's easy to misread. Let me show you what I mean. So often we kind of write the proofs vertically, and we start off with a quantity and we then look at the last line. So it's easy to say b equals 4. That's not true. So it depends on the convention you follow for writing kind of proofs. But I think the one that kind of aligns with Lean is that the right hand side of a line is the left hand side of the next line. So this is b equals a squared, and the next line really means a squared is more than or equal to 2 squared, and then 2 squared equals 4. Let me draw that picture. So we've said b equals a squared is more than or equal to 2 squared equals 4. And what we've not written down, what's almost implicit, because in Lean we'll use underscores, but here it means this thing, a squared, and then 2 squared is 4. So what we've got here is a chain of inequalities. We've got b equals a squared is more than 2 squared, and then 2 squared equals 4. So that's equal sign, more than or equals, equals. And I'll just draw over that just to emphasize it. Equals, more than or equals, 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 more than or equals, equals. So we have to look at those and say, well, what is the summary of these three inequalities? And it's that b is more than or equal to 4, because that's in there as well. If that was equals, then we could say b equals 4, but that's not the case. We do have to be careful with these, because if there's a chain of, I don't know, equals, more than or equals, more than, less than, equals, less than, then it's not so easy then to summarize that into something is less than something or equals something. Sometimes it might not even be possible. So do have to be a bit careful there. Lean will catch it. That's one of the great things about using Lean. It'll catch it if you've made an error. So let's look at some Lean code, and today I'm actually going to live code it. So rather than talk through this code, I'm going to just type it out and explain as I type. That might be a different way of learning. So I'm going to delete what I've got there, and I'm going to talk through what I'm doing. So we've got our objective, which is b is more than or equal to 4. We've got a and b defined as natural numbers. We've got a hypothesis, a given fact, b is a squared, and a is more than or equal to 2. So that's just stating the problem. So we start off with b equals, perhaps. We start off with b because that's the thing that we want to prove something about. So b, what does b equal? Well, b equals a squared, and we have to justify that by, well, it's the first hypothesis, isn't it? There you go. So we're rewriting using this hypothesis. So b is a squared, b is a squared. That's there. But a itself we want to get rid of because it doesn't really help us get to the target. The target is all about comparing b to 4, not b to a. So we want to get rid of the symbol a somehow. Is there another fact that tells us about a? Well, the second hypothesis does. And it tells us that a is more than or equal to 2. So we're saying a squared, so we could write a squared, but the convention is to use underscores, equals, well it's not equals, is it? It's more than or equal to. So I'll just copy that and paste it there. More than or equal to a, or 2, squared. And we have to justify that. It's not a rewriting, it's using what we talked about earlier, that kind of relation, that identity about integers and powers of integers. And we have to use a new tactic actually, because we don't have one that does that kind of reasoning about relations and greater than and less than. So that's what's new today, a new tactic. And it's called rel for relations, like relations meaning more than, less than, greater than or equal to, by rel. And which one are we going to point it to? H1. That should be H2, not H1. There we go. That's good that it catches it. So that's given us a squared is more than or equal to 2 squared. And 2 squared we can easily evaluate as 4. So that's justified by num. There we go. So Lean is happy because there are no messages, no warnings, no errors. So Lean is happy that this is a valid proof that b is more than or equal to 4 given a and b are natural numbers, b is a squared, and a is more than or equal to 2. Great. You can always download the code from the GitHub repository, so it's all available online for free, and you can then have a play with it as well. Great, so that's in the slides if you want a kind of a hard copy. So the new thing there was this rel tactic, which allows us to, which knows about relations like more than, less than, and can do some reasoning with them. It's not perfect, it can't do everything, and if you have an experiment you'll find that some things it can't do easily, but that's fine. It can cope with a lot of the simple stuff, which is what we're interested in. And as I say, the point of this course is not to build an encyclopedic knowledge, but to get comfortable with the concepts of lean math proofs so that we can develop that confidence and then learn more advanced things later if we want to. So this proof, not structurally different from the ones we've done in the first 4 videos. There's a comment at the top, importing the kind of Mathlib library, giving the name, example is a special case, declaring the types of the variables, writing the hypotheses down, the objective, and then line by line progressing the proof argument until we get to the conclusion. And the structure of those lines is always something equals something, or greater than, or less than, and then a justification for each line as well, and it's usually by some tactic. For a beginner course I wouldn't really do this, but just out of interest, let's think a little bit about what rel actually did. So rel is going to, so the rel tactic is going to use a lemma which somebody, or maybe even a group of people, have already written and included in the maths library. And again, this is a little bit more advanced than I would normally do, but that lemma is called nat for natural numbers, and it's got the strange name of power less than or equal to power left. We don't have to kind of talk about decoding that today, but you get the idea. There's powers involved, less than or equal to involved. So it encodes this idea that we saw earlier. N is less than or equal to m means that n to the I is less than or equal to m to the I. So that is encoded and put into the math library for us to use, or for tactics to use. As time progresses, more and more lemmas and theorems are being included in Mathlib. for us to then refer to, or for tactics to refer to. So it's almost building up a body of knowledge that mathematicians can rely on to do everyday proofs themselves. If we look at not the source code for that lemma, but just the way it's declared in the Mathlib library, it's kind of instructive. We won't read too much into it, but there's the name of it. It's about natural numbers n and m. Hypothesis is that n is less than m, and the conclusion is that n to the I is less than or equal to m to the I. But then that would be justified elsewhere in the code, which we're not going to look at today. But it's just interesting and useful to kind of see that the way Lean will work internally is not that different to the kind of code that we've been typing. So you can kind of see there's a lot of similarities there. So that was a first a look at using relations like less than or equal to, more than, at points in the proof that aren't just a conclusion, aren't just about comparing two numerical values. It's about carrying an argument through the proof, carrying inequalities going forward. Now we looked at a very simple one, but you can imagine that it can be more complicated ones as well. But our purpose is to look at simple things. So the easy exercise is also deliberately easy, so that you can focus on practicing the Lean code and not get distracted by the maths. So the idea here is to prove that A is less than C if we know that A is less than B and B is less than or equal to C. They're all natural numbers. Let's draw a picture there. So we know we are given that A is less than B. Let me just check I've got that. And B is less than or equal to C. And our objective is to prove that A is less than C. Now you can look at that and say, yeah, again, really, really easy, isn't it? It's obvious. But the practice that we want to do is turning that into Lean code. So again, I'll talk through some of the thinking without writing the code for you, because that's your task. So we always, by habit, write out the kind of given hypotheses, the assumptions. So A is less than B, B is less than or equal to C, just those over there. Those are the kind of hypotheses. And for our proof, we would start, well, we want to prove something about, so this is the to-do, prove something about A, so we might start with A. And what is A? Does it equal anything? Well, this time there's no equal, this time we say it's less than, so we know it's less than B using fact 1, let's call that 1, and that one 2. And then what do we know about B? Because we want to get rid of it if we can. We know that B is less than or equal to C. So underscore means the right hand side of the previous line, less than or equal to C, using fact 2. And that completes the proof actually, because here we've got A is less than or equal to, no, we've got A, oh, this is where we have to be careful, don't we? Like we said before, A is less than C. So this is one of those things that we said earlier we have to be careful about. So it would be wrong to say that A is less than or equal to C. That's wrong. So A is less than C. That's the correct summarization of that kind of small chain of inequalities. So it's worth just thinking about that. As I said, Lean will catch that. So this proof is not big or complicated, but writing it down like this should then make it easy to write it in Lean code. So have a go, have practice. So to finish there, 2 things I think worth taking away. Number 1, this new idea of using inequalities, relations, in the start or the middle of the proof. That's new for us, and we needed a new tactic to do that, to kind of work and reason about inequalities, relations, rel for relations. And the second thing is just that this, using relations allows us to write more general theorems. So it's quite a powerful thing to be able to reason about. Fantastic. I hope you kind of enjoyed that, and we'll see you next time. Bye.